Hello, welcome to part C of chapter 5. We're going to look at three sections in this part. 5.7 acid phase reaction, gas evolution reaction, and oxidation reaction, where electrons are transferred. I recommend you go back to part P, learn more about the predicting precipitation reaction using the solubility chart, because that's what we will also keep doing in section 5.7, 5.8, that is writing the molecular equation, total ionic equation or complete ionic equation, and net ionic equation for acid-base reaction or neutralization, as well as gas evolution reaction. In this section, 5.7, we look at the acid-base reaction. Sometimes this is referred to as acid-base neutralization reaction. Before we look at the net ionic equation, complete ionic equation, we need to understand what an acid is, what a base is. There are three definitions of an acid. There are three definitions of a base. I'll draw a parallel between those three so that you understand what an acid, according to the three definitions. There is the Arrhenius acid. There is the Bronsted. This is R, Bronsted Lowry. And then there is the Lewis definition of an acid. According to Arrhenius, an acid is simply any, this is defined as any substance that produce or generate H plus when dissolved in H2O or in water. Anything that is that produces hydrogen ion, we call this hydrogen ion in H2O. Hydrogen ion in H2O is called Arrhenius acid. This include side compound as hydrochloric acid, sulfuric acid, SHO4, nitric acid, phosphoric acid, PO4,3. These are examples of Arrhenius. If you look at the chemical formula, they have hydrogen. When dissolved in H2O, it produces hydrogen ion. There is a constant Lowry definition of an acid. This is simply proton. This is proton donor. Sometimes you'll see in exam asking you, how do you define Bronsted Lowry acid? Or Bronsted Lowry acid is dash. You just have to say proton donor. It's different from this. It could be the same compound so long as it can donate a proton. This is just proton, all right? No electron in it, it's just hydrogen. We call it proton. And then Lewis' version of definition of an acid is simply electron pair acceptor. It can accept a pair of electrons. We know hydrogen has two, or to fill the shell for hydrogen ion, we need two electrons. So something such as H plus can accept two electrons to be like helium. In this case, if you accept two pairs, we call this electron pair acceptor. So at the outset, please understand that there are three definitions of an acid, not only that we say Arrhenius definition or anything that produces hydrogen is called an acid. There are three definitions and sometimes can be narrowed down to a specific version on the definition. So if you look at the HCl here, it can produce hydrogen ion. This is called hydrogen ion or proton, H2O. However, it doesn't want to stay by itself in H2O. It gets attached to, if this is the water molecule, we call the model of H2O. It has shown this shape with partially negative, partially positive terminal of the molecule. This is electron-rich portion of the molecule, and therefore, the hydrogen ion produced by acid will get associated with the oxygen atom in water molecule to form what we call hydronium ion. This is called hydronium ion. Okay. Chemists interchangeably use this H plus or this to mean the same thing. In solution, that means in solution of where H2O is used, it produces hydronium ion. So that is how acids are defined. Now, we have what we call monoprotic and polyprotic. You should know that acid can be monoprotic and polyprotic. Poly for many, mono for one. Anything that can produce only one hydrogen, for example, nitric acid, hydrochloric acid, hydrochromic acid. These are monoprotic, but polyprotic include acids such as phosphoric acid, sulfuric acid, HSO4. If you look at the number of hydrogen, it is more than one. Therefore, we call this polyprotic. Right here, polyprotic acid because it has more than one ionizable. To ionize is to produce. For example, here it has ionized to produce hydrogen ion. So if you're given in an exam or a quiz that which one of the following is polyprotic, or if you are asked, give an example of a polyprotic acid, you should know that these are just two examples. Given the formula, you should know what they are. Now, in polyprotic acid, the first hydrogen is ionizable, or it can ionize greatly. It can dissociate to great extent. Fast ionization product is strong. That means can easily donate the first hydrogen. The subsequent hydrogen will be so hard to remove. What that means is, if this is sulfuric acid, first hydrogen will form HSO4 with a negative. If we remove this, this is plus H plus. We have removed one hydrogen. Now to remove this is second ionization. It is very difficult to remove the hydrogen in this species. So I put negative there to form SO4, 2 negative plus H plus. This is the second ionization. First ionization here, it is strong, which means it can easily be given off. There are also three definitions of base, and if we use the same fashion to say here Arrhenius, and then there is Kronstadt, Lowry. These are two people. And then there is the Lewis definition of a pace. So when you look at the paces here too, we can divide according to Arrhenius, according to Kronstadt, according to Lewis. So this one, if you dissolve Arrhenius pace, this is any, you divide this as any substance that produce OH. negative in water. When dissolved in water, produce hydroxide. Remember, this is polyatomic ion for hydroxide. E.g., Na, this is a common Arrhenius space. KOH, it has hydroxide in their chemical formula. You look at sodium hydroxide, produces OH. This, according to Bronsted, a base is proton acceptor. It's the acceptor proton. Doesn't have to have OH. Compounds such as EgNA3 is an example of a Bronsted base because from the dot structure, nitrogen, you don't need to know now, but we'll come back to this later. If you look at the two dots here, it can be donated in coordinate covalent bond. We'll talk about bonds down the line in chapter 8, chapter 9. This will form, or it will accept a proton. This hydrogen here needs 2 electrons, and the 2 electrons are coming from here. See this? It's gonna have that to form ammonium, NH4 positive. It is a proton acceptor. And then this Lewis space is electron. We define this as electron pair donor. This can also be anything with 2 electrons, can donate 2, or even H2O. There are 2 pairs of electrons there. You know, you look at the pairs of electrons for this to be Lewis space. You have to divide according to the number of electrons. In acid-base reaction, we sometimes call this neutralization reaction. And in neutralization reaction, an acid and a base is produced. This is a salt. I mean, in neutralization reaction, a salt and liquid H2O are produced. It's the product. As one criteria, you need to understand that in acid-base neutralization, a salt is produced. This is what I was talking about at the beginning of this session, that you need to be able to write the net ionic equation for acid-base neutralization. Net ionic equation. If we do the splitting, remember what we covered in the previous section, that to generate the net ionic equation, you need to split the aqueous in molecular. So if I'm to write the total ionic equation for this is what's going to happen. You'll have to N, not N, but H. If you look at that, I'll split that to form H plus NO, that is plus 2NO3 negative. I'm going to split right here. You have to see where you need to split. Don't just assume that you'll split oxygen, or, you know, you have to look at the cation, anion, or polyatomic ion, in this case, nitrate, and indicate the physical state aqueous, plus, I'll split this one too into calcium, and this will be ion aqueous plus 2. The subscript changes to coefficient 2 moles of hydroxide. Here, 2 moles of hydroxide is aqueous. Going to, this is a salt, so we will split also that to Ca2 positive aqueous plus 2NO3, this is nitrate aqueous, plus 2H2O. Recall, we do not split solid, liquid, or gas, only the aqueous. So if I cancel out the spectator ion, I'll see that calcium on the product side and the reactant side will go away. Next is the nitrate. If you look at the nitrate here and the nitrate here, they look exact same. So I'm going to cancel that. I'm going to cancel that. So net ionic equation, equation. This one here is generated from here that what remain is 2H positive aqueous plus 2OH negative aqueous going to 2H 2, this is liquid. And since you divide everywhere by 2, this will cancel out, and that's why we are here. These guys, you don't need to memorize or read the PowerPoint slide and expect that, I'm going to ask you the same thing. It's about the concept. How do you write the net ionic equation? You need to have or start from the very basic foundation of having a balanced molecular equation. You need to balance the molecular equation, split the aqueous in the molecular equation, and cancel the spectator ion on either side in order to end up with the net ionic equation. Revisit again from the last section, part B. So these are the products of acid-base reaction, a salt and liquid H2O. So if I'm looking for, or if I'm asked to classify a reaction as acid-base neutralization or reaction, I'll have to do is one criteria is to look for product liquid. It can be any salt, sodium chloride, or nitric acid in this case. Now, some others use hydrogen ion or hydronium ion interchangeably, all right? Whatever referring to an acid as a substance that produces hydrogen ion. We can use hydrogen ion or hydronium. It's the same thing because hydrogen combined with liquid H2O to form hydronium ion. Now, I've talked about acids which ionizes. Polyprotic acid ionizes as well, and the first ionization is large for polyprotic acid. These are just few examples of acid: hydrochloric acid, nitric acid, sulfuric acid. This is polyprotic, and then acetic acid. See, those are most common acid you will encounter. I define phase. Of course, you should know now that there are 3 definitions of a phase according to Arrhenius, according to Bronsted-Lowry, and according to Lewis. Okay, so phases are substances that react with or accept hydrogen ions. They increase the concentration of hydroxide when dissolved in H2O. So if I look at here, react with or accept, this is Bronsted definition of a phase. Proton acceptor, proton donor for Bronsted-Lowry definition of an acid, it's donate hydrogen ion, or proton donor for phase, say proton acceptor. Anything that produce or increase the concentration of hydroxide is Arrhenius base. Some substances do not contain hydroxide ion, yet they are considered as bases, such as ammonia. It will generate hydroxide in liquid H2O. Those are Bronsted definition of an base and an acid. Now, we have strong acid, strong base, weak acid, weak bases. What determines that is that the strength of an acid acid or base is defined based on degree of ionization, In other words, you may have a concentrated weak acid. So do not confuse the strength with the concentration. You can have a concentrated weak acid, or you can have a dilute strong acid. So strength has nothing to do with the concentration. The strength of an acid is defined based on degree of ionization. So strong acid or strong bases, these are 100% ionization or dissociation. That means a strong acid or strong base, 100% ionization. E.g., HCl can ionize 100% or NaOH for a base 100%. Whereas weak acid, here, weak acid is about 5% ionization. What we mean by ionization is how many hydrogen ion can be produced. Using acetic acid, which is an example of a weak acid, acetic acid, which is weak. So this is acetic acid, which is a weak acid. If I have 10 molecules of this, what I mean by 5%, or if I have 100, let's say 100 for easy calculation, 100 molecules of this, 95%, 95 will be innate will just be the same as the original. It doesn't dissociate, it doesn't ionize. It doesn't split to produce the hydrogen ion, whereas 5% will produce CHCOO negative and hydrogen ion. That's what is meant by ionization, or 5%. It produces the conjugate phase, the conjugate acid. That's the difference between a weak acid and a concentrated acid. A weak base and a concentrated base. You need to remember the examples of strong acid. You see here, completely dissociated for strong acid. That means it's 100% ionization, whereas weak acid are partial ionization. So here are examples of strong acid, strong base I've seen in Chem Chem 2 courses, that by the time you get there, you'll be expected to know examples of strong acid, examples of strong bases. All right, nitric acid, hydrochromic acid. These are strong bases, these are strong acid. Strong acid are considered as strong electrolytes, yes. Whereas weak acid are considered as weak electrolytes. Remember the electrolytes we learned earlier on? All right, so you can also apply here that strong acid are strong electrolytes, weak acid are weak electrolytes as well. This applies to bases. This is, I think we looked at earlier on the ionic compound. Remember, ionic compound are strong electrolytes, they ionize, they conduct electricity, and none of the ionic compound are weak electrolytes. Molecular compound, the reason why we are revisiting that is because we are at acids, and acids are strong electrolytes. strong acid, strong electrolytes, weak acid, weak electrolytes, just to revisit the electrolytes versus non-electrolytes, in particular looking at the strong acid and weak acids. In neutralization reaction, an acid and a base react or neutralize each other, and a salt and H2O are produced. These are the product of acid-base neutralization. Just like the precipitation reaction for acid-base neutralization, you should be able to write the molecular equation, which should be balanced, complete ionic equation and net ionic equation. I'll just maybe look at a few examples on how we end up with the net ionic. You look at this is molecular equation right here. This is the complete ionic or total ionic equation where the aqueous species are split. We split these into aqueous hydrogen ion. There is chloride on the first reagent. Second reagent, there is sodium ion and hydroxide. We don't split the solid. Remember solids? You don't split the solids. You don't split the liquid. So this is going to be the complete ionic. If we cancel out the spectator ions, this is the net ionic equation for this reaction between HCl and sodium hydroxide. So for acid-base neutralization, we should be able to generate the three equations. It's just diagram on what happened at the molecular level. Here are a few common acids, common bases. Please commit to your memory. These are just few common acids you need to remember. And some of the formulas might look different from what you know, especially like acetic acid. It's the same thing. I know some of you may think, what is going on? It's different from this. It's the same thing, all right? Sometimes they may have a condensed formula, C2H, how many hydrogen, this is 4, and then O2. It's the same thing. You should be well-rounded in writing the formulas. Acetic acid, 2 carbons, condensed formula, 1 plus 3 for hydrogen, and then 2 oxygen. Compared to what I do have here, it's the same thing. If you add 1 hydrogen plus 3 gives you 4, and 2 carbons, 2 hydrogens. The reason why you have this hydrogen here is it's ionizable. It's ready for ionization. For bases, these are common formulas as well as their names. You need to learn those as well. This is just an example on, writing the net ionic equation. This is balanced molecular equation, right? The net ionic equation. This balance. Now for weak acid, should be able to do the same thing. Look at the problem number 6163 on page 208. These two problems are good for practice writing the net ionic equation, complete ionic equation for acid-base neutralization. 5.8 is gas evolving reaction. There's some reaction which produce gas. You'll see in the lab, some reaction produce gas as evidenced by the phasing. Remember the evidence of a chemical reaction phasing, and phasing indicates that a chemical reaction or gas is being produced. In the same way, we will have to learn how to write the net ionic equation for gas evolving. And there are few specific gases we need to learn in this chapter. Hydrogen sulfide, these are produced by the sulfide. Sulfide, I will say this is one. Sulfide. You see, IDE, I should have just minimized this so that you see, yeah, sulfide. Produce hydrogen or sulfide gas. The acid plus sulfide. Remember acid base? Here is an acid reacting with sulfide. It produces hydrogen sulfide. This is hydrogen. So when you look at the chemical formula for all sulfide, they produce a salt and hydrogen sulfide gas. There is for CO2, all right? And this is for carbonates and hydrogen what? Hydrogen carbonate. Remember carbonate? So this type of class of compound produces hydrogen, no CO2 gas, and liquid H2O for carbonates. So carbonates produce CO2 gas. This is gas producing reaction. HCl, you see the facing indicates that gas is produced. These are the four types of compounds you need to remember what they produce. Sulfides produce hydrogen sulfide. So this is potassium sulfide. Carbonate and bicarbonates. This is the intermediate product which produces carbon dioxide. This is a weak acid produced, it breaks down to produce CO2. Sulfides, which is different from the sulfides here. Bisulfides produce sulfur dioxide, and ammonium produces ammonia gas. Four, 1, 2, 3, 4. So there are four classes of gas evolution reaction gases. Reaction in aqueous solution which produces gas. By now you should know the formulas. This is sulfide, SO3 is sulfide. This is ammonium chloride, use ammonia, and the sulfide carbonates produces CO2. These are the gases we are referring to in gas evolving reaction, evolution reaction. Problem 67, 68 on page 28, please practice with those. And lastly, I want us to look at 5.9 oxidation reduction reaction. This is the last section in chapter 5. There are some reactions which involve transfer of electrons. We call those reaction oxidation reduction reaction, or simply it is referred to as a redox. You'll see this. These are two reactions taking place at the same time, and you should know what they are. It involves transfer of electron, reduction, oxidation. Two reactions taking place. There is oxidation, which is loss of what? Loss of electrons, loss of electrons. Whereas reduction, gain of what? Gain of electrons, gain of electrons. If you want to remember these two reactions, just say oil rig, oil rig. So that you say oxidation is loss of electron. And then reduction is gain of electrons. And remember, electrons are negatively charged. They are negatively charged. So this is what I'll use to define until I commit to my memory definition of oxidation and reduction. When you see this even two reactions taking place, one species is losing electron, the other species is gaining. For example, in the reaction between sodium plus chlorine gas, let's say this is solid, to form NaCl, you should be able to see which one is gaining. There is electron transfer from sodium to chlorine to form positive and negative. That one electron is gained by chlorine, making sodium less or electron deficient by 1, and positive negative to attract. That's how we end up with that. Sodium chloride because of transfer of electrons. So the redox is a type of reaction which involves transfer of electron. And traditionally, it used to be, reduction used to involve only oxygen. It has been expanded to include also electrons. So if you look at this, these are examples of reaction where oxygen is involved: rusting, combustion, all right, of hydrocarbon, which we looked at earlier on, is transfer of electron. So you need to know how to define the oxidation. You need to be able to define reduction. Remember the oil rig. This is what I was saying. So instead of just memorizing this, I'll use this to understand. Oxidation is loss of electron. Oil, oxidation is loss of electrons. Reduction is gain of electron. You need to remember that. And if you look at here, the electrons are, or one electron has been transferred from sodium to, and of course you need to balance the equation, which means for every 2 sodium, 2 electrons are transferred. So sodium is losing and chlorine is gaining. Loss is oxidation, gain is reduction. And look at how the equation has been written. Maybe that. Well, reduction does not have to be complete transfer of electron from one species to another, but it could also be an even sharing of electron, an even sharing, such as in HCl, right? In this compound, there is an even sharing, and an increase in electron density indicates a reduction. If I look at electron poor portion of the molecule, electron rich portion of the molecule, there is some reduction in a way, because one side of the molecule is electron rich, the other side is electron poor. Using the electron potential map, this region with blue color indicates electron deficiency, positive. Therefore, reduction is taking place here as well. Yeah. Reduction is taking place here as well. Now, I think we should be able to define, now you should be able to define oxidation, reduction. And oxidation take place typically between metal and a non-metal. Sodium is a metal, fluorine is a non-metal. If you look at the starting elements, they are free elements, but we end up with ions. This is positive, this is negative. We talk about being ions. We end up with ions with negative, positive. We know positive, negative to attract. Now, in order to understand, how many electrons are being transferred, or if oxidation is taking place, sometimes you may be given a chemical equation and you are asked, is this, or what type of reaction is this? Is this single replacement? Is it double replacement? Is it decomposition? Is it combination? For you to make a conclusion whether it is redox, you have to assign oxidation numbers, all right? It is a way of electron bookkeeping in redox reaction so that we see which species is losing, which species or reagent is gaining, and how many electrons are transferred, all right? So we will look at how to determine the oxidation numbers. And remember, chemists assign those numbers to each element in a reaction. Each element in a reaction, you may have a compound, but you need to assign each compound, each element in that compound, what we call oxidation number. It has nothing to do with the periodic table. Don't think that you can use the periodic table and say the oxidation number. Well, you may use that, but not all the time that is going to work. I'll show you how you can use the periodic table and then you calculate. So you have to be careful when to use the periodic table to assign the oxidation number. So this is just a chart. Oxidation number is just a chart it will have for an element if it was to share shared electrons in a compound. You'll notice that the sign is written in front of a number as opposed to what we know from the charges be on the right side of the number, oxidation number. And there are rules for assigning oxidation number, which you need to learn, you need to commit to your memory. It's going to come back in the next quiz, in the next exam, and even you'll encounter in the Alex Homework assignment, assigning oxidation state. You need to learn these rules. You may use 4-pi-6 index card. One, free elements have an oxidation state of 0. Free elements such as let's say this is sodium, that means 0, even a hydrogen cars, even chlorine cars, so long as it's in elemental state, the oxidation state is 0. Rule number 1 is 0. So copper, chlorine, don't think that this is the only one. It's got to be elemental form. Monoatomic ion have oxidation state equal to their charge, all right? Mono, that means one, is not polyatomic. So if you look at calcium, it's in group 2, potassium, lithium, sodium, all right? They all have positive 1, positive 1, positive 1. Not 9, but positive 1 right here. For sodium, they all have. So I'll use the periodic table. For this particular, you have to look at the number. Calcium is in group 2, 2 positive, so it's going to be plus 2. Group 2. Chlorine, negative 1. Oxygen, negative 2. Negative 3. You have to look at in what group does it belong to. Now, the sum of oxidation state for all atom in a compound is 0. So if you look at, let's say, sodium carbonate, or sum of oxidation state adds up to 0. Let me show you, let's say, H2O, how can oxidation number or sum of oxidation numbers be 0? It's because when you assign the oxidation number, the last element, for example, here, take first priority in assigning the oxidation. Other elements you can calculate. For example, here, oxygen equals to negative 2. And hydrogen is positive 1. So this is plus 2, negative 2. You end up with 0. That's why sum of the oxidation state adds up to 0. It could be also C, let's say CO2. The first element right here, take first priority. So I'll say X. Say let X be oxidation number for carbon because we don't know it can take any form. Don't use the periodic table, you need to do the calculation. So if this is x, you say x plus negative 2 times 2 equals 0. I have to equate to 0. You see here, 0 for a compound. So this is going to be x minus 4 equals 0, which implies x equals to 4. X equals to 4. So you have to do the math for compounds. You have to do the math for compound and equate to 0. Last element, take first priority by assigning the oxidation number as if it is monoatomic. Oxygen is in group 6, it has -1 common oxidation number, Now, for polyatomic ion, you equate to the overall charge. For example, here, let's see polyatomic ion such as CO3. If you are asked to assign the oxidation state to each one of them, you say let X be oxidation number for carbon. So I'll say X minus 2 times 2 times or negative 2 times 3, not times, but 2 times negative 2 times 3. Negative 2 is the oxidation state for oxygen. We don't know for, we don't assign the first element. We don't know, it can be +4 -2. So equals to now -2. We equate to overall charge for polyatomic ion. So X this is plus, it should be plus here. So X equals to +6 and oxygen equals to -2. This was asked to find the oxidation state for each element in carbonate. So if you look at this nitrate, for nitrate here, show you what is happening, NO3 negative. The first from the left, from the right, sorry, take first priority. This oxygen, say this is X. This is how you do, let X be oxidation number for N, that is nitrogen. Since I already know for oxygen, this will be X plus -2 times 3 equals to -1. So X minus 6 equals to 1, which means X equals to 6 minus 1, which is +5. You see how you end up with that? This is +5. So without necessarily memorizing that, always nitrogen will be +5, oxygen is -2. You need to do the math the way I've done here in order to do what? In order to determine the oxidation state. One last one is, let's say we have sulfate, for example, SO2. This is oxygen, sulfur. So let's say X. If X is the oxidation number for sulfur, you say S, no, which is X, it will be X plus -2 times 4. I'm looking at this -2 here, which is right here. -2 here is for each oxygen, which means X minus 8 equals -2. Implies X equals to 8 minus 2, which is equals to +6. So this is the oxidation number for sulfur. You do the same thing for any other element you are given. Please learn the criteria by which you assign each element, and then you do the what? You do the math. There are some common, properties. For example, here group 1 metal will always have oxidation state for +1 in all compounds. There are some exception in other groups. All right, group 2 metals have oxidation state of +2. Learn that. For non-metals higher on the table, they take priority. So you need to know where they are in terms of non-metals and look at their oxidation number. So once you know how to assign that, you can calculate the oxidation number of any element on the periodic table. All right. So learn the rules and how they are applied in determining the oxidation state. Now, apart from defining the oxidation and reduction, you need to be also, you should be able to identify reducing agent and oxidizing agent. Reducing agent is the species donating electron. Oxidizing agent is the species gaining the electron. So once you know what is oxidized, what is reduced, you need to be able to identify oxidation, oxidizing agent, and reducing agent. For example, here, if you look at the reaction, like the way it is, you can't tell which one is the reducing agent or oxidizing agent, or which step represent reduction, which step represent oxidation. Remember rule number 1, oxidation state for elemental state for compounds will always be 0. So carbon has oxidation state of 0, state of 0. However, in the compound, if we do the calculation just the way I walked you in the previous slide, it will turn out that sulfur has an oxidation state of -2, +4. So here is reduction. You see from 0 to -2, that means you have added 2 electrons, or we have added 2 electrons. But for oxidation, we are losing 4 electrons. So if I look at this, carbon is the reducing agent. It reduces. To reduce is to add electron into. So C reducing agent. Whereas S is oxidizing it's making the other species to lose electron. I was writing without having that. This is what I had on the whiteboard, that from calculation here, this is oxidation, yet oxidation loss of electrons. So it's going to add electron to sulfur. reducing agent. It's adding electron. It reduces. How do we know? It has become positive, which means we are less by electron. Oxidizing agent, that means it's making the other species to lose electron. Oxidizes. Sulfur oxidizes carbon. Carbon reduces sulfur and so forth. So that's how you look at the oxidizing agent, reducing agent. Here is an example on assigning oxidation state. You can read on your own. Let's just do this real quick. Determine the oxidation number of each of atoms in the following compound. So remember what I said, you'll assign this one first before you do that. Then you do the calculation, you equate to 0. This will take first priority. Negative, you cannot have positive and positive, by the way. So this is negative, this is positive. You do the calculation. All right. When you have to, you say 2x equals to 10, and then you do the math from there. So that's how you assign the oxidation state for each element in a compound. So what I'll do is, this will take first priority before I do the math on that. Don't memorize these things, guys. You will miss it if you memorize. You have to do the calculation, just the way we did before, and you should be able to do the same thing as we did before. Now, oxidation of metal in aqueous solution is just an example of displacement reaction or single replacement reaction. We'll look at the activity series later. Look at problem number 69, 71 on page 208, assigning the oxidation state. So remember what I said, oxidation, reduction, reaction take place at the same time. I've explained what is reducing agent, oxidizing agent. Reducing agent adds electron to the other. Oxidizing agent accepts the electron from the other species, oxidize. So reducing agent is oxidized, and oxidizing agent is reduced. So learn those until you understand the difference between reducing agent, oxidizing agent. What is being reduced, what is oxidized, and then you will not miss it. So that is all for redox reaction. Please read more, practice until you understand, until you nail it down. Well, let's shift gears to single replacement reaction. This chart right here is called activity series. An activity series is a list of few selected elements on the periodic table, not all the elements on the periodic table, but few selected metal except hydrogen. There is hydrogen here. So not all of them are metal, listed from the most active to the least active. So from the most easily oxidized to the least oxidized. This table will not change. I will give you in the exam, you should be able to know how to use in predicting whether the reaction will take place or not for single replacement reaction. And again, anything above an element will replace anything below. For example, lithium replaces all what you see here on any reaction. So the most reactive, the least reactive. Perhaps maybe looking at an example on how they use the activity series, it will be clear. All right, which metal is most oxidized? That means it can easily be meant to lose electron. And if I look at sodium is all the way up there, the rest they are below. Chromium and arum. Arum is right here. Chromium is there. It's not visible. So you look at the position where they are. Now, I guess the example on single replacement will help. But before we do that, does a reaction occur when aqueous nickel 2 chloride is added to zinc? So you need to see if zinc is so strong I mean, if nickel is so strong, it won't let it. So I need to have nickel above zinc in order for it to say no, there is no reaction, or there will be reaction. So if I look at zinc is here, and nickel, zinc and nickel. So zinc and nickel. So zinc will replace nickel because zinc is above nickel. So in other words, it's not strong enough. It's not strong enough. Now, learning check, which element is reduced and which element is oxidized. You need to know what is reduced, what is oxidized. By looking at this example, let me show you how you can determine what is reduced and what is oxidized. So if we have 3 moles of iron, 3, this is iron, 2 nitrate, not 3. This is E, is aqueous plus Al. This are 2 there, plus A, and by the way, this should be 3 as well. It cannot be 2 here, got to be 3. Remember that. So here is 3. So how do you know which one is to reduce, which element is reduced, which one is oxidized? It can't be on the product side, I mean reactant side. This is how you look at it. If something doesn't change, that means not going to participate. For example, here nitrate will be the same. But if I look at the oxidation state from here to here, this is 0 to plus 3. 0 to plus 3, so this is oxidation. This is plus 3, 0. This is, we are adding electron. Oxidation reduction. Which element is reduced? That means we are adding electron. Is reduced to F. Al oxidized. Al aluminum is oxidized. You have to assign oxidation numbers in order to see which species is gaining, which species is losing, and then make a conclusion which one is expanding, which one is reducing. Now, before you look at the modules in Alex, module 5 in Alex, I want to solve one more problem on single replacement reaction, and in particular, the reaction which produce gas. Example is Fe plus HCl. The reason why I want to do this is you'll see this kind of equation in the lab. If I look at the activity series, we need to look at the activity series here. Iron is above hydrogen, so reaction will take place, and it can be iron 3 or iron 2. It doesn't really matter. Let's say iron 2 plus hydrogen gas. It gives hydrogen gas. All acids keep hydrogen gas, and what this means is this is more active. It is more active compared to hydrogen. It is above it, so it will replace for single replacement reaction. And all acid give you molecular hydrogen. This hydrogen gas, which is hydrogen gas, which is the atomic note H2O. This is yeah, hydrogen gas. It's not 1H. I've seen student giving me 1H. And by the way, the equation has to be balanced. So here we have a 2, 2. So the equation is balanced. Unless it is ion 3, you'll do the same thing over. Sometimes you may have it as no reaction. So please practice on end of chapter problems as well as self-test quiz in the text before attempting module 5 on Alexa.